Welcome to this NPTEL lecture on principles and techniques of modern radar systems. We were discussing match filter. In the previous class, we have seen the match filter, it output maximizes SNR. Today we will see what else match filter can do. Actually, today we will see that it is not only maximizes SNR, but its output is nothing but a correlation of the received signal with the transmitted signal. So, that is the beauty and that we will explore today. So, again we are considering the previous things, that there is a radar is transmitting a bandpass signal xt. Now, we have received it, this delay, round trip delay is T naught, and so we are calling the received signal corrupted by noise. So, that we are writing x I t minus T naught, because it is delayed, and also n I t is the noise that has been added input. So, if this is the match filter, so obviously we can write what will be the output. Previous day we have seen match filter and we have seen the match filter output. So, we can definitely write that, or let me explicitly define it mathematically. What is x I t? So, x I t is nothing but x t minus T naught. Actually, it will be obviously have an amplitude factor, but also may have a phase factor, that for simplicity I am now not taking. So, this plus the n I t. Actually, there is something here that I should have, but it is immaterial. If you assume also, no problem. Now, what will be the output of the match filter y t? That we learnt that this is given by minus infinity to infinity x I u h t minus u du, where u is a running variable. So, the output, since it is a integration, so the output will be function of time, that is y t. Okay. So, I can write, give the equation names, that the last time we ended at equation 17. So, this equation let me call equation 18 and this one is equation 19. So, now we know the match filter. So, please refer to equation 15 where match filter was there. I can see that what was the match filter, that was the causal match filter. So, if we put that, so from equation 15 we can put that, what was that? That was h t was nothing but x star tau naught plus T naught minus T. I am recalling that tau naught is the round trip delay for the signal from transmitter to coming back to the receiver, and that is T naught, and tau naught is the extra delay added for make the impulse make this match filter causal. Okay. So, h t was this, but I need a h. You see that in case of thing, this is h t minus u. So, can I write, if I write it as h u, this will be x star tau naught plus t naught minus u. Okay, as simple. Then let us make a substitution because this is tau naught. So, let us make that, let tau naught plus t naught plus t, sorry, this tau naught plus t naught minus u, let us substitute is for understanding, otherwise those who can do for them. So, if you do this, then we know what is u. U will be tau naught plus t naught plus z, sorry, minus z minus z, and then du will be equal to dz, du will be equal to minus dz. So, that thing you can use. So, what we can write that h of, I will have to finally make this thing h of tau naught plus t naught minus z, that will be x star z, and so h of minus tau naught minus t naught plus z, that will be x star minus z. So, putting this, that h u, so actually I need h of minus u thing. So, that if we do, you can easily do this. This is simple math. So, you will see that now your y t, that will be minus infinity to infinity x I u x star t minus tau naught minus t naught plus u du. Okay. So, let us call this equation 20. I think I am clear that if you just do this substitution, it will come in terms of z, then it will be easier for you to do. So, after that again putting the back the value of this, you are getting this y t. Now, let us recall what is the definition of cross correlation between two complex function. So, cross correlation between two complex function, let one function is f t, another let us say g t. So, what is the cross correlation? This definition I am now writing, that cross correlation is generally denoted by this R f g, their cross correlation. This all of you have done in your basic network class or etc. So, this we know is can be written in many ways. So, I can write like this, G star tau. Now, this R f g, that is a function of time. So, that is why the running variable we are changing G star tau f of t plus tau d tau. Or if you want conjugating the other, you can also write previously what we wrote. Okay. So, this is G conjugation, or I can make the conjugation here also, that you can make F star tau G T plus tau, as I think this also is true. So, comparing these, we can now easily understand that what is our y t. So, y t in terms of this, I can write that it is cross correlation between x I and x, you see. So, and what is the variable? That t minus tau naught minus t naught. So, this now we have previously seen that we can combine these two and give that time we have given a name. Actually, if I put that, because T naught is the delay and tau naught is the causal thing and T naught is the round trip time delay. So, let us give it a name capital T naught. So, if I substitute this, then this can be written as R, the cross correlation between the received signal and the transmitted signal, and this can be written as T minus T naught. That means, I can say that what is match filter output. So, let us first give it a number, because I think now is the time for giving it a value 21. So, what equation 21 is very important. Equation 21 says that, let me show the what is equation 21, that it says that match filter output is the cross correlation between the received echo signal x I and a delayed replica of the transmitted signal, because this is delayed by how much? Capital T naught. So, a delayed replica and this. So, this is an important thing, that is why this topic name is that match filter output is nothing but a correlator. What it correlates? The received signal, it correlates with the transmitted signal delayed by T naught. So, it is great that it is basically this correlation. So, if you really have that, you have got a received echo from a transmitted signal, then the correlation value will be high. So, this is a now let us, with this knowledge, let us put that what happens when the range, we know the range information of a closing target. So, we will do that what is the range of a closing target, we know it is given by R t range, and that is we know R naught minus V into. So, do not think is a function, that is why I am writing into T minus T naught. So, where V is the constant radial velocity, constant we are assuming that the target has a constant radial velocity, and what is r naught, that time we have said, again I am writing, it is nothing but the initial range. So, a moving target that then will have this range at any as a function of time, and we know also what is the expression of r naught from our, if the target moves with that, what is r naught? R naught is nothing but T naught C by 2, T naught C by 2. So, that we also know, because it is a half delay. So, you see that what is the range, we know this. Now, actually the radar echo signal, that is band pass signal. So, XIT is band pass signal, transmitted signal was also band pass. So, band pass signal we know actually will, when analyzing we express it in terms of complex envelope. So, that will do, that will simplify our thing. So, we can write that XIT is what? It will be, if suppose we take it as a in phase and quadrature, because some receivers work on that principle, IQ receivers. So, in that case it will be XIT cos 2 pi FCT minus x QT sin 2 pi FCT. Instead of writing e to the power, I am writing like this, that this is XIT, and in terms of this I can write, and so it's, let us say that XIT is band pass. So, if I say that phi IT is its pre-envelope. All of you are familiar with this, that we express pre-envelope concept, and the real part of that actually is the complex envelope, which is a low pass filter. So, and let us say that complex envelope of these. So, complex envelope we generally put a tilde over the thing to say that it is a complex envelope, like phasor type of thing. So, XIT let us say is the complex envelope. So, what is the relation? Instead of writing this, I can also write XIT as a, in terms of complex envelope, that is nothing but real part of phi IT. And what is phi IT? This is just for recall, that is why I am not giving any equation number here. It is, all of you can see this in your communication things. Hekin, Simon Hekin is a good book where these concepts are quite well written. So, e to the power j 2 pi f c t. Actually, the beauty of complex envelope is that this is the complex envelope, and XIT any time you can give, but you can see that complex envelope is free of the carrier, because the carrier is not carrying the information. It is carrying the information, but information is not here, information is either in the phase or in the amplitude of the carrier. So, otherwise carrier is not useful for us. So, complex envelope is carrierless, that is why it becomes a low pass signal. So, if we analyze complex envelope, we get all the information of the signal. So, this is the means of throwing away the carrier, that is why it is possible. Also this you see that carrier and the complex envelope, they are multiplication and they are separately written, whereas if I write like this, you see carrier and the other part, signal part, that is not separate. That is why this is a better representation than this one. So, that is why we will not do this, but this is a thing. Now, let us specialize. First, I will see a stationary target, we will develop the mathematics, then we will go to the moving target. That means, what I wrote as RT, now my range is fixed. Let us say at stationary target, there is a target at a fixed range. So, R naught, there it is. So, let me write this, that now I will discuss a stationary target. So, to start with, I am having this simplified assumption, later I will remove that assumption. So, stationary target, before that just give this thing a name. So, let us say this is our equation 22, because we will be heavily using this, the actual signal, real signal and the complex signal, what is their relation in terms of the frequency, carrier frequency. Okay. So, for stationary target, I come back. So, what is the received deco? XIT for stationary target, that is nothing but x t minus t 0, and that we can also write that what is t 0, that we know, t minus 2 r 0 by c. Okay. So, now what is the complex, in terms of complex envelope, I can say that it is real part of x I, or instead of x I, if I write it directly in terms of a, so I can say real x t minus t naught e to the power j 2 pi f c t minus t naught. This I can write by using 5. So, x I t is what? Real part of, I should have written x I t, but I know that for stationary target x I t is x t minus t 0, that I am using here. Okay. So, this equation we should give a name, just this is our equation 23. So, we can now say that what is the complex envelope for the received deco. So, I can say that what is the complex, just look at here. So, complex envelope of the received deco is what? Just looking at here, I can say x t minus t 0 e to the power minus j 2 pi f c t naught. Just suppress the carrier part. So, this is important, that what is the complex envelope of the received deco in terms of the transmitted signal complex envelope, this is their relation. So, this should be given a number 24. Okay. So, you can see that received complex echo is more than just the delayed version of the transmitted complex envelope. It has an additional phase shift. How much is the phase shift? Minus 2 pi Fc T naught, and the beauty is that contains actually the range information that I will show that. So, you see that received echo signal, just not the transmitted signals delayed version, it also has a phase shift, additional phase shift. So, what is that phase shift? Let us call this phase shift as what is the color, phi naught. So, if I call it additional phase shift, then I should write additional phase shift, because the circuits, or rather the receiver circuitry, they only see the complex envelopes, they analyze on the basis of complex envelopes. So, what they will do, that phi naught is what, from here you can see that, because phase is time invariant. So, here it is minus 2 pi f c T naught. So, we know the value of T naught. So, what is T naught? I can say 2 R naught for a stationary target, remember, and that is what? That is nothing but now C by f c, that will be lambda naught. So, or lambda c. So, the carrier lambda and then multiplied by 2 R naught. So, I can say that this is another equation, that phi naught. So, additional phase shift is how much? It is minus 2 pi by lambda c into 2 R naught. So, this is again an important relation, because for a stationary target also you see we have an additional phase shift. So, now the question is a very small change in range. Suppose the range R naught is changed, but you see that change in range R naught, that can give rise to a large change in the phase. So, that is why this phase term, that will be treated as a random variable with uniform PDF in the interval 0 to 2 pi. This we have seen many times in the A, that if the range is small, then also this phase can be significant, and you know that due to modulo 2 pi nature. So, it becomes a random variable. So, this is the thing, that phi naught is random, and generally it is modeled as a uniform thing. Also, this phase needs to be unwrapped, that means modulo 2 things should be understood, and that is called unwrapping. Okay, but let us continue our discussion, that we are actually trying to find out that match filter output, what are the phases of that output, what is the magnitude part of that output, that we are trying to find for a stationary target. So, we can refer to equation 19 and we can put these values, because now I know the received echo. I also know that what was our equation 19. You can see that in equation 19 we have seen that what is the match filter output. If you give an input, then for a match filter what will be the output. So, that we have done. So, I can say that, let us go to the next page, that match filter output is always y t is equal to minus infinity to infinity x I u. Now, I will, so this is also the complex envelope of the match filter output. So, that is h t minus u du. So, this is from 19, equation 19 gives us this. So, now here we can put that we have the definition of match filter, that means what is this in terms of the signal, that is given by equation 15. So, we can put equation 15, from equation 15 we will get the value of this h t minus u, and from just equation 24 you can see equation 24 gives us x I. So, I will write that from 15 you can get this value, from 24 you can get the value of x I, its complex envelope value. So, if we put that here we get what that. So, now everything is complex envelope, that is why I am redoing everything. So, it will be minus infinity to infinity, then x u minus t 0 e to the power minus j 2 pi f c t 0 h, still I have not put the value. So, h t minus u du, but in 15 we have that value, that we will have to do and then we get something, but h we know. What is h? We know that h of t, that we know, that is this is the definition of the match filter. That means, equation 15 tells us this, but we will have to find h t minus u. So, that we will do, but time is up. So, that we will take up in the next class. Thank you.